we've done confidence intervals. Right? And the idea behind a confidence interval is that we are trying to trap the true population mean. So that if we have a 95% interval, we have a 95% chance that the true mean of the population is in there. The edges for this are 2.5 and 2.5, and this is alpha level. This is the chance of making a mistake. And it's invariably 0.05. All right, it can be anything you want it to be, but a 1 in 20 chance is pretty common. For a hypothesis test, we are concerned about the ends and not the middle. What we are trying to do is test a sample against a proposed value. We have an idea that the true mean, the true but unknown population mean, is 69. All right, it doesn't matter how we arrive at this. Somehow it has come into our head that the true population mean for whatever it is 69. And we want to test that hypothesis. We get a sample with a mean of 75. The sample size is 71. And the standard deviation for the sample is 45. So for the hypothesis that the true mean is 69, I get a sample, and if I looked at it from a confidence interval, I would look at, is 69 in that interval? For the hypothesis test, we want to look at, is 69 in the ends? Is it so far off from our sample that we don't believe that the mean could be 69? So instead of looking at the middle, we're looking at the ends. And for this, do you believe that the average could be 69? Is 69 so far from our sample mean of 75 that we don't believe it? It's not too far off. So this is what a hypothesis test does. And all the numbers that we had on this sheet where we were doing confidence intervals, we can pretend like they're hypothesis tests. And there is absolutely no difference except what you're looking at. And this is invariably the result of an experiment. For a confidence interval, it's observational. I get a sample and I can get a confidence interval. And that sample can come from anywhere. For a hypothesis test, it is a controlled experiment. And what you're looking at is, does this treatment change something? And the typical example is corn yield. I don't know what we'd do without corn in statistics, because it is the old standby. the very first experiments were done in agriculture. So that all of the statistics techniques we have were developed in agriculture. And the deal is that if I'm doing a corn yield experiment, I have to control every factor except what I want to test. And usually the example is a fertilizer. If I put fertilizer on this, and I don't put it on this, is there a difference in the yield? And my test is the fertilizer effective? So the experiment is, does fertilizer work? Everything in the experiment has to be controlled except for the treatment, the fertilizer. I have to have the same kind of soil fertility. I have to have the same kind of machinery. I have to use it the same amount, use it the same way. Everything has to be the same except for the fertilizer. This is difficult to do even in agriculture. So if I take a field and look at that field, I fertilize half of it and don't fertilize the other half and compare the results. Even then, the halves of the fields aren't the same necessarily. So there's a lot of work that goes into making sure that whatever the treatment is, that's the only thing that influences the result. The confidence intervals, it's the same kind of test. We look at it from a little different direction, but for the confidence interval, if I want to estimate corn yield, I just go measure corn. And I go out in the field and I take plots and I measure the yield of the corn. And I can say, yeah, the corn yield is this. For this field, this is my best guess. So the experiment has much more control. And the only thing that matters is the fertilizer. Experiments are used for medical treatments. If you have whatever, and you've got high blood pressure, and they have a new blood pressure medicine, does the medicine lower the blood pressure of the people that are given? And you have to have exactly the same. The people have to be exactly the same, the ones that get the medicine, the ones that don't. This is so impossible that there is an endless supply of high-paid advice on how to do it. Some experiments are difficult to do. The corn yield, no problem. That's why everybody uses it for an example. If we had to use high blood pressure medicine, we've got to have someone sort through a bunch of candidates and randomly assign them to a treatment. And the people that I'm using have to have the same weight. They have to have the same body mass index. They have to eat the same thing. They have to sleep the same amount. They have to do exactly what you want. The best way to do an experiment like that is with time travel. So you could take these people, give them the medicine, and see what happens. Then you go back in time, you've got those same people, and you don't give them the medicine. And you see what the difference is. And so all of this is really, really difficult to manage. And these things are an absolute pain to handle. We were testing erosion on roads in forest. What kind of equipment do you drive on the road in a forest? And the equipment is huge. It's big enough so that it can walk up to a tree. You drive it up to a tree, you grab the tree, and you cut it off at the bottom. Then some of them, you hold that tree and you drive to another tree. And you do that until you've got enough to make a bunch, and you lay it on the ground. And then somebody comes along with a skidder with a grapple on it, grabs it, picks it up, and drives off with it. So you've got this big equipment driving around to the trees, and it's got to go to every tree. And then you've got these skidders that drag the wood out, and they have huge tires. They weigh a whole bunch because they're going to be dragging whole trees. And you've got whole trees dragged along the ground. So what you want to look at is what kind of erosion do you get with this kind of equipment versus that kind of equipment. One of the differences in equipment is how many tires it has. So that some skidders have 4 tires in the front and 4 tires in the back, so that it spreads the weight out as much as possible. A tracked vehicle is sometimes used. This is like a tank. And the advantage of that is you don't roll. You have the weight of the machinery distributed across the tracks. And as the thing rolls, they move along the ground and they don't push into the ground and spin. You can't hang up a tank, which is why they use tanks. So that the kind of equipment is different. So to test the erosion, you have to have somebody use this equipment, somebody use this equipment, and you need to have the circumstances as much as possible the same. So that you can say the runoff is less here than it is there. And they actually use what they call dirt bags for these experiments. And this is an actual thing you can look up, and they sell dirt bags. And you put them alongside and divert water from the roads into the dirt bag to see whether you get more dirt in the bag from this area than you do from that area. So all of these things are very, very controlled, or it won't work. So that these things are very specific in how they're set up. For what we want to do with a confidence interval, we go get corn. We measure something. We measure the height of people. We don't care where those people come from. For this, we have to be very specific in the experimental setup. And for this, there are proposed outcomes, so to speak. And this is called a null hypothesis. And it's called a null hypothesis because it's H naught, H0 as a subscript. And the null hypothesis for the corn yield could be the mean corn yield is less than 100 bushels per acre. The null hypothesis always represents the status quo. I'm doing an experiment to try and prove that I am wrong. The alternate hypothesis, this is called HA or H1 sometimes. You see them both ways, is that the mean for the corn yield is greater than 100 bushels per acre. So that the alternate hypothesis is what I want to demonstrate. Right? I can't prove anything with statistics. I can't prove that the fertilizer works. All I can say is, as far as I can tell, I can reject that the fertilizer doesn't work in favor of the alternate hypothesis that it does work. So that this is very clear cut. It's either this or it's that. I got a confidence interval. I got 95% chance that I got the real mean. The experiment is the same thing, except everything is controlled, and I only have, is it this or is it not that? And I can have different kinds of null hypothesis. This is called a one-sided hypothesis, because I am looking at one side. Is it 100 and less, or is it more than 100? So I've got this on one side or that. If I'm doing a two-sided experiment, and this is much more difficult to set up. Suppose I'm making ball bearings. And if you look down the road here, there's a plant that makes bearings. They don't make ball bearings necessarily. There's all kinds of bearings. But if I want to experiment with a process that makes these bearings, I have, are they too big or are they too small? They have to be within a very narrow range of size. So that my null hypothesis is basically, and this is not in numbers, the bearings are just right. This is Goldilocks. This bed is too hard. This bed is too soft. Or this bed is just right. So a two-sided hypothesis is a Goldilocks hypothesis. It's not this, it's not that, it's just right. So that the way I have to set it up, the null hypothesis, in numbers, and I have to put it in numbers because I have to test it, and statistics is the only way I have to test it. Goldilocks tried this bed, tried that bed, this was bad, too hard, too soft, this is just right. I can't say just right. I have to say the mean of this population of bearings is 9 millimeters. Supposing I'm making 9 millimeter bearings. The alternate hypothesis is that they are not 9 millimeters. It's too big or it's too small. So this is a two-sided hypothesis. And the deal with this is, where do I say it's too hard or it's too soft? For the one-sided experiment, I have to have a critical region or a rejection region. For the corn yield, I have to say I reject the null hypothesis. And This is what the alternative does for you. The alternative always points to the critical region. What corn yield do I say fertilizer works? 101. Fertilizer work? Could that be an accident? 102. What if I got 150? Yeah, fertilizer worked. Here's 100, and here's 150. At what point do I say the fertilizer worked? This brings back the alpha level. My cutoff for this experiment, saying the alpha level is 0.05, the chance of a mistake, when I get a result that is in the tail of my sample. I have a sample average, and this is exactly the confidence interval, except I'm using one side, and my cutoff is 0.05. Right here on this one I had, what did I have? Well, let's make one up. Sample average is 105. Standard deviation is 15. I have a sample size, my number of plots where I've tested the corn, of 30. What's the standard error? It's all the same. Confidence intervals, the experiments, all the calculations are the same. The difference is purely in the interpretation. What's the standard error? Standard deviation divided by the square root of the sample size. 2.74. My alpha level is 0.05. Here is my continuum of corn yield. My average is 105. Is 105 big enough to say it's different than a 100? This is a two-sided or a one-sided experiment, and all I need to do is, here's 100. Is 105 in the tail of 5% mistake? The t-value, it has a t-value just like a confidence interval, is the sample average of 105 minus the hypothesized value of 100 divided by the standard error. 5 divided by 2.74, 1.82. Go back to the empirical rule. Where's 95%? 2. And minus 2. Here, I have one tail. I don't need 2.5 here and 2.5 here. I'm going to put all 5% in my rejection region. And the alternative points to the rejection region. It's on the upper end. I need to compare 1.82 to the cutoff of 95%, but it's all on one side. So I have 0.05 here and 95% there. What is the probability of getting a t-value of 1.82? I want to know whether 105 is sufficiently different than 100. So my t value is 1.82 equals t dot dist 1.82. How many degrees of freedom? Degrees of freedom is, what did I say? Or sample size is 30. Degrees of freedom 29. I need cumulative probability. I need a 1 in there. T dot dist 0.96. I can do this two ways. One, I can look at it from the 95%, or I can look at it from the 5% rejection region, which is the way that it's usually done. So that I need 1 minus this equals 1 minus that. And as usual, I have a whole lot more decimals than I ever needed. I have 1.82 is at the 96% position from the left, and at the 4.04% or 4%, 0.04 on the right. So this is a one-tailed test. Here's the t, this is 0. Here is 1.82. The area to the left of 1.82 is 0.96. The area to the right is 0.04, basically. Does my result of 105 fall into 0.95 here and 0.05 there? Yes. It's big enough. Look at it from the other direction. At the 0.05 level, alpha equals 0.05. This is my chance of a mistake, and the alternative always points to the rejection region, so it's pointing up. It's pointing up. The alternative is greater than 100. What is the actual cutoff for 0.05 in the tail? Basically, I want to know, I have a number here at 0.04. It's within the 0.05 tail. I'm going to reject the null hypothesis and say the fertilizer works. What is the cutoff for 0.05? Use Excel. We need equals t dot inv. I need 0.95 because that's the way that it works. It always comes from the left. Here, t.inv 0.95. This is going to cut off 5% in the upper end with 29 degrees of freedom. And I get basically 1.7. So if I look here, this cutoff is 1.7. Right, now, this is two ways to look at the results. One way is I got a number 1.82 that's bigger, that's further out than 1.7. I reject the null hypothesis in favor of, yes, the fertilizer works. The other way to look at it is I got 1.82. Where is it really? It's at the 0.96 level. 0.04 in the tail. 0.04 is less than 0.05. I am past that criteria. This is called the p-value. In statistics, if I'm doing an experiment with alpha equals 0.05, I'm perfectly within the boundaries to say 1.82 is bigger. Therefore, I reject at the 0.05 level. The other way is to say, this is at 0.04. What do you want? What if you wanted 0.01? And this is a perfectly valid and sometimes used criteria. If this is at the 0.01 level, do I reject? What's 0.01? What's the 0.99 cutoff? Look at Excel. If I'm using alpha equals 0.01 equals t.inv, 0.99 now. I can use 0.01 and just change the sign. I'm going to get the same number. It would be negative. If I use 0.99, 29 degrees of freedom, what's my cutoff now? 2.46, 0.99. Here's the cutoff, 2.46. This is 0.01, alpha equals 0.01. Is my 1.82 in that tail? It's back. So I have a stricter criteria for rejection. If I do this test at the alpha equals 0.01 level, I would not reject. I would say, no, the fertilizer doesn't work. And this is a big deal in statistics. In some organizations, if you do the experiment and you say 0.05, good, I reject the null hypothesis. I don't care where it is, it's inside the 0.05. But somebody says, well, that's not much of a criteria. We need more probability, less chance of error, 0.01 chance of error. I can't change it. I did 0.05. That's my cutoff. If you have an experiment, you can say, this is what I got. What do you believe? Do you want 0.01? You don't believe it. If you want 0.05, that's good. I can say reject at the 0.05 level, or I can say I got 0.04, it's your decision.